Hey Calcutane, this is Rocky, and we're going to talk a little bit about antiderivatives. So what would an antiderivative be? Well, what's a derivative? A derivative corresponds to slope, right? You take a function, and to find a derivative at a point, you just look at the slope at that point. It's the instantaneous rate of change, right? If the slope is very steep, then that means at that point, the function is changing very fast. If the slope is almost horizontal, then that means that the function is changing very slowly at that point. So let's look at what it would mean to do the opposite thing, to take an antiderivative. Or, well, we've been thinking about derivatives to the first derivative, second derivative, third. What would it mean to take a negative derivative, derivative -1? So let's look. Okay, so here, if we have a map that corresponds to position, so the x-axis is time and the y-axis is going to be position, you have a particle that moves up slowly and then it moves down slowly as time moves on. That's position. It's measured in meters. The derivative of that is going to be velocity, meters per second. That's how fast it's moving. And then the change in velocity is acceleration, meters per second squared. So it seems that every time we take a derivative, right? Velocity is the derivative of position. Acceleration is the derivative of velocity. We add a seconds factor at the bottom when we're talking about the units. What would it mean to take an antiderivative? So say we're starting with velocity. What would it mean are we able to recover the position? So here's an example. Let's suppose that we're given a function, f of x equals x. Suppose we're looking at velocity. So this is how fast something is moving. So it's moving, and at time, which is going to be the x-axis, when time increases, it's getting faster and faster. So if it's getting faster and faster, it's not going to move linearly. It's going to move more like this. It's going to start kind of slow and then move fast. It turns out that the antiderivative of this is actually going to look like this. Look at how the slope changes. At time equals 1, the slope, this is actually going to be 1 slope. At time equals 2, this is going to be a 2 slope, etc. At time equals -2, this is a -2 slope. And what does this correspond to? Well, if we look at our original function, let's consider the area under the curve. All right, so if we're looking at the area under the curve from 0 to 2, this area of this purple triangle, it's going to change if we increase from 2 to 2.2, which is going to be right there. We're going to have added this little smidgen. And that little smidgen changes sizes right here. This little smidgen is much smaller than from here to here. So it actually turns out that we can visualize, just given a function, which corresponds to velocity, it's the derivative, we can visualize the antiderivative by thinking about area under the curve. And that's going to be it. So it turns out that if we put both of them, then it turns out that the area under the curve, so the area of this purple triangle, is going to correspond to the value of this parabola. So the area under the curve of this triangle is actually going to be equal to this point. And similarly, if we increase up to here, the area under the curve of this whole purple region is going to correspond to this point. And so that's antiderivatives. We're going from velocity to position, or acceleration back up to velocity. It's a way to get one up. Now here's something to think about. What would be the antiderivative of position? The units, if we notice how when we add antiderivatives, we take away a seconds factor from the bottom. So the integral, the antiderivative of position, is going to be measured in meters times seconds, not meters over seconds. maybe you can think a little bit about what would metered seconds correspond to. Anyways, I hope you learned something from this, and good luck.